U-substitution is actually a technique of integration. So this is something that you would use throughout this semester. It's going to show up back again in chapter 7 when we do trigonometric integration, chapter 10. So you will see this over and over. The technique is related to a differentiation technique where you is involved, a substitution of some sort is involved. Calculus 1. Do we know that technique? What is it?
I want to say when you have something with like different variables, when you have a function with different variables, you substitute u in.
Okay, how about this? So I've got e raised x. Do we know the derivative of e raised x? Yes, what is it? Same e raised x. E raised cosine x. What is the answer?
Is it negative sine x e raised to cosine x?
Wonderful. Yes, and you going to be a mathematician. I'm going to start pushing instead. Because I want. Well, the answer is not this. If life were to be that easy, I would not be in this galaxy. I'd be somewhere else. That is a function. And your answer is correct. I'll get to you in a second. If I call u to be cosine x, then that would become e raised u. Agreed. The original variable is x with me. That x went into another function to form cosine x. Yes. Now you have to take e raised cosine x, come up with its derivative. So one function is inside another function. Yes, no, maybe. For instance, if I said g of x is e raised x, f of x is cosine x, I can rewrite e raised cosine x as g of f of x. Yes or no? I can't. That operation had a name. Oh, we'll get to that later.
I was going to say chain rule.
Start, but very good, very good. Isn't it? Do you agree? They're saying chain rule. But that's the derivative part of things. This has a name.
It's a composite function.
Very good. This is a composition. G composed F. So that. If you compose G with F, while G of x is e raised x, f of x is cosine x, that's what we will get. Good? That is the composition. Anytime you have function within a function, what rule would you use to find the derivative? Chain. So, U-substitution is the reverse technique that people would use when chain rule went into play. Good. There are other cases, and I will explain those as I go along. Clear so far? I'm going to start with a simple example. X plus 1 square. What is the answer? or how would you go about finding the derivative? The approach, one way, is this. Evaluate that x plus 1 squared is simply x plus 1 times x plus 1. FOIL, you'd end up getting x squared plus 2x plus 1 times dx. Agreed? As long as you have terms in addition or subtraction, you can distribute the integral. Yes, you could take the integral of the first term, second term, third term. You don't have to memorize, you get to have the table of integrals, but the integral of x raised n is x raised n plus 1 divided by n plus 1. So I can distribute the integral because things are just added based on what I wrote. What is the integral of the first term? X squared. X cubed over 3. Next one. Next.
2x squared over 2, so just x squared.
2 is a constant, so it'll stay. And x, the power is 1. 1 plus 1, 2. X squared over 2. Because what about the last term?
X.
0.
It's x.
X.
We want x.
You know, distribute, you're taking 1 times dx. Dx, integral of dx is x. So, x, good so far. Plus 3. Easy enough. Now, what if I have this instead? X plus 1 entire thing raised to the power of 16 and dx. Let's start simple. Do you really want to take the approach that we took over there? I love algebra, I love math, but I'm not going to do it. It's a waste of time. And I don't know if you get it right even after trying. I know easier ways to get the answer, but I won't try. So there has to be a different approach. So if you look at this function, you have that inner box and then raise 16. So there is something inside something else. Yes? So I'm going to start with the outer part. So hypothetically speaking, let's say this is a side note, not part of the solution. Suppose I have x raised 16. And some function comes in, knocks the x out, replaces it, you will get x plus 1 raised 16. Agreed? What is that function that's coming in? Do you follow my question, or do you want me to repeat it? X plus 1. Very good. If x plus 1 comes in, knocks the x out, you'd end up having x plus 1 raised 16. Agreed. It's pretty much a composition. So whatever function that enters in step 1 is your substitution. So u is x plus 1. The requirement is if you have u, you take its derivative. What is the derivative of u with respect to x? 1. Derivative of that is 0, so just 1. I can rewrite du equals dx. Good? With me so far? So if I have a u, it's right here, and you can replace whatever whatever expression that you have in the integral in terms of u. So this would become u raised 16. Yes. Whatever else that stays in the integral must match up to du. If it doesn't, then your substitution would not work. So once you rewrite this, whatever leftover part that you would have here must equal du. Does it equal du in this problem? Does it?
Yes.
Yes. So du is just dx. That one is easy to integrate. What is the integral? Instead of x, I've got u. So the integral is
U to the 17
okay,
over 17.
u raised 17 over 17. N is 17. And in turn, instead of x over here, the integral has u. Is that it? No, some say no.
Fuzzy.
Plus c, but is that it? Michael says no. Why?
Because it's a u instead of an x.
It has u instead of x. You've got to go back. So replace u by your substitution. X plus 1 raised 17 divided by 17 plus c. So u substitution is great and all, but it'll only work if it follows a sort of a template. Once you pick the right u, whatever that's left behind after that substitution in the integral must equal to du. If it doesn't, then something is wrong. Either you are making a mistake or that particular integral cannot be integrated using your substitution. Good? Golden rule of thumb. Once you replace u, whatever that remains has to become du. If it doesn't, probably not going to work. Clear? Now, another thing to pay attention to when we are doing u substitution, as you go from here to there, you have successfully converted an integral that is purely in terms of x to an integral that is purely in terms of u. Do you see any x here? No, they cannot stay behind. So if you go from here to there, u substitution worked. Integrate, replace the u back, and you're done. More, but before I end, here is a question. Let's see if we can answer. We're not going to do this. We can try this next time. You can try it at home if you want. Or now, Let's answer a simple question. Is U-substitution possible? No. Xavier says no. Okay.
Shouldn't you be able to substitute sine x for u?
Yeah, I'm asking you, so it is possible? I forget your name, but it's
Anna?
Anna. So Anna says we can substitute. So if I start with u equals sine x, what is du over dx?
Cosine x.
With me so far? What is du? You rewrite it. Du cosine x dx. So 3 is outside. E, I'm going to replace with the u that I identified. So u. Once I do that, whatever that is left behind in that integral, does it match up with du? And do keep in mind, it can differ by a constant in the sense you could have a number here. We can do that algebra. I'll do the problems on that next time. But the moment I did this, whatever that is left behind in the integral, does it match up with du? So all of that became that. What did I leave behind? This. Does it match up with du? That. So U-substitution is possible. Good. If you can't go past this step, then if you can't get rid of that x in the integral, then there is a problem. You are either making a mistake or your substitution is not feasible. I urge you to write it carefully, explicitly, solve for du, and rewrite this integral instead of skipping steps, because that's how you make mistakes. Once you become an expert, go for it. But as you learn, don't make that mistake.